This video presents the information that is obtained by Proton NMR and how that's applied to the structure determination of small organic molecules. To begin with, there are three different types of information that are obtained from basic Proton NMR spectra. The first is chemical shift, the second being integration data, and the third being spin-spin coupling or splitting data. And I'll go through these sequentially, starting with chemical shift. Recall from the previous video, and by the way, if you haven't watched the previous video on the theory behind NMR spectroscopy, you should do that first before you watch this one. So recall from that video that protons in different chemical environments resonate at different frequencies. Now, and an example of an NMR spectrum is given here. Now, we need some sort of standard to measure those resonances by. And the standard that's typically used, that's most commonly used in Proton NMR spectroscopy, is tetramethylsilane, which has this structure right here. And the reason, well, we'll talk about the reason why tetramethylsilane is used at another time. So this is our TMS peak. Let me label that here. TMS is of course, our abbreviation for tetramethylsilane. And all the other resonances of protons in a molecule in different chemical environments, different types of protons, are measured versus TMS. TMS is chosen because it tends to be on the farthest side of the spectrum. There are very few molecules that, or types of protons that resonate at higher field, which is over in this direction in an NMR spectrum. So we compare the resonances of different types of protons in a molecule to TMS. So there's a problem here, and that is there are a lot of different types of NMR spectrometers. And those different types of NMR spectrometers will have often, in many cases, different magnets, different strengths of magnets. Now, the same protons will resonate at different frequencies. We saw that in the previous video on spectrometers with different field strengths. And so, for example, if you've got a 100 megahertz spectrometer, you might have a proton, a type of proton that resonates in a molecule at 100 hertz downfield. This is known as downfield from TMS. On that same proton in the same molecule would resonate 500 hertz downfield on a 500 megahertz spectrometer. So if you're using a different field strength in Proton NMR, you're going to get a different chemical shift. This is what the chemical shift is, the position of a resonance relative to TMS. You'll get a different chemical shift in hertz depending on the different type of magnet, the different strength of magnet you're using in the spectrometer. And this is a problem because we want consistent data. We want to get the same information, the same data, no matter what spectrometer that we use. And so there's a way of standardizing all of this data so that we don't have this problem. And that way is using what are known as delta units, or also known as parts per million. So we do this for consistency. And delta, or parts per million, is defined as is calculated as the chemical shift in hertz from TMS, so that would be 100 hertz here, divided by the spectrometer frequency in hertz. So if we've got a chemical shift of, for example, 100 hertz on a 100 megahertz spectrometer, so that goes in the denominator. 100 times 10 to the 6th is 100 million. That's 100 megahertz. Times a million gives us our chemical shift in delta, or parts per million. And the reason it's called parts per million is this 10 to the 6th in the denominator here. So what does that do for us? Let's take a look. Oh, before I do that, let's do the same calculation with our resonance on a 500 megahertz spectrometer. So remember, the same protons will resonate at 500 hertz on a 500 megahertz spectrometer as resonate at 100 hertz on a 100 megahertz spectrometer. So we have 500 hertz in the numerator divided by 500 times 10 to the 6 hertz for the spectrometer frequency in hertz. That's equivalent to 500 megahertz times a million gives us 1 delta unit. So you see the chemical shift of both of these is the same on both spectrometers now if we use these delta units, also known as parts per million. So let's take a look at what an NMR spectrum looks like now in both parts per million, or hertz, and in frequency. And so our x-axis, our abscissa, is now delta, or parts per million. The y-axis is intensity, and we'll talk more about that when we get to integration. And so here are the delta units, and the typical Proton NMR scale ranges from about 0 out to about 12. I only went to about 10 here, parts per million. The farther away from TMS you get in the left direction here, the lower the field strength and the higher the frequency of the protons that are resonating. So actually it's usually one or the other depending on the type of spectrometer that you're using. So just to give an example here, for a 100 megahertz spectrometer, these are the different frequencies in hertz that correspond to each one of these delta units, or parts per million. So each delta unit is 100 hertz, so 100, 200, 300, and so on. With a 500 megahertz spectrometer, each delta unit is 500 hertz. We saw that up above here. So one of the things that's interesting to note here and important to note is that there are more hertz between these delta units for a stronger magnet. The 500 megahertz spectrometer has a much stronger magnet than a 100 megahertz spectrometer. And so between each of these delta units on a 100 megahertz spectrometer, you have 100 hertz in frequency units. Between each of these delta units on a 500 megahertz spectrometer, you have 500 hertz. That tells us that on a spectrometer with a more powerful magnet, like the 500 megahertz spectrometer, you get better resolution. You get peaks that are separated more clearly on a stronger magnet. This is the reason why institutions that need high resolution in NMR will pay lots more money for a bigger magnet, for a stronger magnet, more expensive NMR. And again, this is also important. This is very, very commonly used. The farther away from TMS you get, the lower field. That corresponds to lower field strength on the old continuous wave spectrometers. The older spectrometers varied the magnetic field strength that would sweep from low field strength down here to high field strength over here. That's why this is known as low field. This end of the spectrum is known as low field, and this end is known as high field. Newer spectrometers, the FT-NMRs that we've talked about, maintain a constant field strength and pulse a broad band of RF radiation. So this x-axis can refer to the field strength, and that's usually what it was in the older spectrometers, but it also refers to the frequency, and we see that in the hertz here downfield from TMS of the applied RF radiation. So we have higher frequency RF radiation downfield, and we have lower frequency RF radiation upfield. And we'll talk about why that is in just a moment. I'm now going to talk about the physical basis for chemical shift differences between protons, as well as common factors that influence those chemical shifts. So to begin with, electrons around nuclei, and there's always electrons around nuclei, shield the nuclei from the applied magnetic field. So the more electrons you have around a proton, for example, the higher field it will resonate. Okay, so the more shielded it will be, and it will take a higher magnetic field to get those protons to resonate. Remember, this is the high field part of the spectrum. This is why TMS is chosen as a standard. One reason why TMS is chosen. Silicon, remember, this is tetramethylsilane. You had a silicon bonded to 4 methyl groups. We saw that structure previously. Silicon is very electropositive, and therefore the protons on the methyl groups in tetramethylsilane are highly shielded. There's a lot of electron density around them. So there are very few things that resonate higher field in organic chemistry than TMS. So it's a very good standard to use. It's way over on the high field end of the spectrum. So we have some protons here. Methane, the protons in methane resonate at 0.23 delta units. That's way up here on the high field end of the spectrum, so these are relatively shielded protons. Now, electronegative substituents nearby an observed proton will de-shield it. That means it's pulling electron density away from the protons, moving its resonance downfield, and we see this in this data here. A bromine is more electronegative than a hydrogen, so when we replace one of the hydrogens in methane with a bromine, look what happens to the chemical shift. We go from 0.23 to 2.9, which is a very big change in chemical shift. So we're going from here down to here, going downfield. oxygen is even more electronegative than bromine, and so replacing the bromine with an OH group where the oxygens bond to the carbon bearing the hydrogens that we're observing. We're observing these underlined hydrogens here. The resonance moves from 2.9 to 3.3, so we've gone from here to here in our spectrum, going from bromomethane to methanol. And to compare the halogens here, this is good data for determining the effect of electronegativity differences on our substituents on the chemical shift of nearby protons. So we got methyl iodide here. The protons on the methyl iodide resonate at 2.1. We go to bromine, which is more electronegative. Now we're out to 2.7. Still farther downfield is chloromethane. The protons on chloromethane at 3.05. And even farther downfield are the protons on fluoromethane. And we know from general chemistry as we go down the group, so this is in reverse order, as we're going down the group in this direction, the electronegativity falls. So fluorine's the most electronegative of the halogens, and it has the biggest effect, moves the protons on fluoromethane farther downfield than the least electronegative, iodide, which is only 2.1 relative to 4.3 for fluoromethane. So finally, I should mention, since they're so common, in NMR spectroscopy, alkyl groups, alkyl substituents, and that's what R is here, it's an alkyl substituent, are slightly electron withdrawing, so we can consider them to be very weak electronegative substituents. And so a methyl group bonded to a carbon, the protons on the methyl group will, a monosubstituted carbon bearing protons will resonate at about 0.23, which is very close to methane. It's actually the same as methane. Now when we disubstitute a methylene group with two carbons, that moves the chemical shift a little bit downfield. And when we try to substitute a methyl group on a methine, it's still a little bit farther downfield. So now for our first spectrum of an actual molecule, at least my best representation of that. So this is methyl 2,2-dimethyl propanoate. And I've color-coded the two different types of protons here. So we've got a proton that's closer to an electronegative oxygen, and we've got protons that are on carbons bonded to a less electronegative carbon, less electronegative that is than this oxygen. So note what the being close to the oxygen does to the chemical shift of these protons. So the green resonance here corresponds to this methyl, the protons in this methyl group. The blue protons are this resonance right here, very far upfield compared to this one. So the difference in the chemical shift of these two different types of protons is a function of this electronegative oxygen here. These protons are closer to this very electronegative oxygen, therefore they resonate farther downfield than these protons that are not as close to these electronegative oxygens. So there are not electronegative substituents as close to these protons as these protons. So again, to summarize, nearby electronegative substituents move our chemical shifts downfield, farther away from TMS. Now for some other important points about chemical shift. Protons in the same chemical environment have the same chemical shift, and actually we saw that in that previous spectrum. I'll scroll that down in a second. By chemical environment, I mean chemically equivalent protons. And to give you an idea of what that means, if you were to exchange two protons in a molecule, those two protons would find themselves in the same chemical environment. So protons on a methyl group are always chemically equivalent because there's free rotation around this bond here, this carbon-oxygen bond, or if it were a carbon here, that carbon-carbon bond. Remember, there's free rotation around, at normal temperature conditions at least, around single bonds in linear molecules. And so because there's rapid rotation around this bond, these protons equilibrate in their chemical environment. They, on average, have exactly the same chemical environment, therefore they're chemically equivalent. We see the same rotation around these bonds. So this entire tert-butyl group is rotating, as are these methyl groups. And so if we were to make a model of this and rotate around these bonds, you would find, since there's rapid rotation, that each one of these hydrogens, these 9 different hydrogens here, are in exactly the same chemical environment. So we see one resonance for those hydrogens, and we see one resonance for the hydrogens on this methyl group. So that's what we mean by chemically equivalent protons. And I've given you a few more examples of that down below. So we're talking about some symmetry in molecules now. These protons are symmetrical. They're all the same, as are these protons here. So some other molecules with symmetry, cyclohexane. There's 12 hydrogens here that are all in exactly the same chemical environment. You see one single resonance for all 12 protons in cyclohexane. Similarly, something like ethane. A molecule like ethane, we know what ethane is, will have one single resonance. So all 6 protons resonate at the same chemical shift. So there's rotation around this bond axis here, the carbon-carbon bond axis, and that rapid rotation makes certain that all of those hydrogens are exactly the same chemical environment. Remember, I should probably mention here that, remember, there's actually 2 different types of hydrogens in a cyclohexane. We've got, and the most common conformer of cyclohexane, of course, which is chair cyclohexane. There's the axial and the equatorial hydrogens. So why is there only one resonance? Because at room temperature, the 2 types of axial and equatorial hydrogens are interconverting rapidly due to the rapid ring flip here. So rotation around bonds is one thing that induces this symmetry and gives us, in many cases, chemical equivalence between protons, symmetrical protons. Another thing I should mention about the substituent effects for the effect of electronegative substituents, that is, on chemical shifts, is that they are additive, and we see that with this data here. Chloromethane, the protons in chloromethane resonate at 3.05 delta, or ppm. We substitute one of the hydrogens to make dichloromethane, so we've added another electronegative chlorine, and the 2 remaining protons resonate farther downfield. We put 3 chlorines on a methane, and now we're all the way down to 7.26. And you'll note here, remember that methane is about 0.23 ppm, that's CH4. So there's about a little bit more than 2 delta units between methane and chloromethane. We see that same, very close to 2 delta units between chloromethane and dichloromethane, and again, very close to 2 delta units between dichloromethane and trichloromethane, again talking about the chemical shift of these protons. So each chlorine that we add is shifting the remaining protons on the methane about 2 parts per million downfield. So substituent effects tend to be additive. Finally, increasing distance between the electronegative substituent, which I've represented as X here, and the observed proton reduces the effect on chemical shift. So if the electronegative substituent is on the carbon bearing the observed proton, that's this one right here, we can see a significant downfield shift in parts per million in delta from about 1.1 to about 4 parts per million downfield. Adding 1 extra carbon, so this is the alpha carbon and this is the beta carbon. Now putting the electronegative substituent on the beta carbon has a much smaller effect on chemical shift. So instead of greater than 1 part per million, we're down to less than 1 part per million effect. So moving the electronegative substituents farther away from the observed proton reduces the effect on the chemical shift of those protons. In addition to electronegative substituents, there's another very common and very, very important structural feature that can strongly affect the chemical shift of observed protons, and those are pi electrons, as in double bonds, triple bonds, aromatic rings, and so forth. And so I've given you some examples of protons whose chemical shifts are altered by nearby pi electrons. Normally, not always, but usually, pi electrons de-shield nearby protons, and often strongly. We see that here. So here this is an allylic proton. It's 1 carbon removed from a double bond. And it's downfield. If this were a methyl group, this is a full, even more than a part per million downfield from a simple methyl group. If this proton were on a CH4, recall a methyl proton is about 2.23 delta units. Putting this methyl group in a carbon-carbon double bond moves it more than a part per million downfield. The effect is even stronger when we have a vinyl proton. That's a proton that's attached to an sp2 hybridized carbon. So an alkenyl proton resonates way downfield at 4.5 to 6.5, and that's the farthest downfield of almost anything we've seen so far except for the proton on trichloromethane chloroform. Even farther downfield are protons on benzene rings, which generally resonate around 7, 7.2, 7.5, but they can, depending on the substituents on the benzene rings, they can resonate in a fairly broad range from about 6.5 to 8.0 parts per million. Even farther downfield are aldehydic protons. Not only do you have the pi electrons here that are moving this, deshielding this proton, we've also got this electronegative oxygen, so aldehydic protons resonate way downfield around 10. There's only about one common type of proton that resonates farther downfield than an aldehyde proton, and that's a proton on a OH group of a carboxylic acid. So why do pi electrons have this effect? Why are they usually deshielding? I have illustrated that here for a carbon-carbon double bond, and this would be the same for a carbonyl as well if we had an oxygen here. The applied magnetic field from the spectrometer, B0 again, we saw in the previous video that an applied field can induce a current in a coil. This applied field induces a current in our pi electrons, so the little orbitals containing the pi electrons act like a wire. The applied field causes the electrons to circulate, the pi electrons to circulate. Circulating electrons, again, as we saw in the last video, create a perpendicular magnetic field. And so the circulating electrons circulating due to the applied magnetic field from the spectrometer produce their own little magnetic field. And this magnetic field tends to orient in such a way that it reinforces the applied field. And so this induced magnetic field is reinforcing the applied magnetic field from the spectrometer, thus deshielding the proton, making it resonate at lower field strength or higher frequency farther downfield. So we see here, this is way downfield from an alkane proton. Same thing in a benzene ring. Anytime you got pi electrons, you have the same phenomenon occurring. So here's again our applied magnetic field. It induces a pi electron current, this flow of electrons, that produces its own little induced magnetic field that no matter where the proton is on the ring, reinforces the way these things orient, the way this ring current is induced, reinforces the applied magnetic field, causing these protons to resonate farther downfield. So that's the effect of pi electrons on chemical shift. The next thing I'm going to discuss now is the second type. We've talked about chemical shift, the factors that influence chemical shift. And chemical shift gives us very important structural information. It tells us the different types of chemical environments, the numbers of different types of protons that we have in a molecule. So each different type of proton will give us a unique resonance, and those resonances will be in regions that, as we see here, are characteristic of protons in unique chemical environments. So we get lots of structural information from chemical shift data. Another type of information that we get from Proton NMR is integration, which I discuss here. Integration refers to the fact that the intensity of a resonance, remember the y-axis here in our spectrum is intensity, is proportional to the number of protons in a molecule. And this also gives us important structural information. It gives us the ratios of the different types of protons in a molecule. And I've given you a good example of that here. We saw this molecule, this spectrum earlier. So in this molecule, we've got two different types of protons, two different chemical environments. We've got this type of proton resonating here, and we've got these 9 protons that are all chemically equivalent resonating here, farther upfield. So the spectrometer, when it takes the NMR spectrum, will integrate the area beneath these resonances. And the ratios of those integrations are proportional to the intensity of these resonances. The ratio of those integrated areas gives you the relative ratios of the different types of hydrogens, of protons. And so we see the ratio here. We got 9 of these protons and 3 of these. So there's two ways that spectrometers often report these integrations. Newer ones often will give you a little, they'll mark the region where a resonance occurs below the spectrum, as I've shown here, and it'll give you a little number there. And we see the same thing with this resonance here. And the spectrometer will give you a numerical ratio between these integrations. And so you'll see something like 3. You could see something like 3.1 or 1.09, something like that. Sometimes they're not whole numbers. Little errors in the integration sometimes. But the ratio is essentially 3 to 1, and that's the ratio we see here. It's 9 to 3, which reduces to 3 to 1. So it doesn't give you the actual number of protons in the integration. It gives you the ratio of the different types of protons, the numerical ratio, the simplest numerical ratio typically. Another way that these integrations are often shown on, and this is I think truer for the older spectrometers, are as little integration curves. And so the way you deal with these is I would always use a ruler. I'd typically use millimeters. And I'd measure from the bottom of the little curve here to the top, write down the number of millimeters, do the same thing for the other integrations, and you end up with a ratio of millimeters that would be a 3 to 1 ratio. So this might be 12 millimeters, and then this one would be 4 millimeters here. So integration tells us the relative ratios of each different type of proton in a molecule. So now we turn to the third and final type of information that we get from Proton NMR. Unfortunately, this is the most difficult to understand, but it's incredibly powerful for determining structures of molecules. And this often, for larger molecules, is even more important than chemical shift data. And this is known as spin-spin coupling, also known as splitting. So to begin with, when you take a spectrum of a very simple molecule like bromoethane, we see in bromoethane there are two different types of protons. The protons on this methylene are closer to the electronegative bromine, so we know those will be farther downfield than the protons on the methyl group. The problem is, and by the way, these methyl protons are all identical, so there's free rotation around this carbon-carbon bond, so they're all in the same chemical environment, as are the two protons on the methylene in the same chemical environment. So from what we've discussed so far, we'd expect two single resonances for these two different types of protons. That's not, however, what we see. What we see is something a little bit more complex than that. We see for the methyl protons 3 peaks in a 1 to 2 to 1 ratio, and for the methylene protons we see 4 resonances in a 1 to 3 to 3 to 1 ratio. So what's going on here? This is our first exposure to spin-spin coupling. The protons on the two adjacent carbons are splitting each other. They're coupling. So how does this happen? What's going on physically? It turns out the protons on adjacent atoms have their own little magnetic dipoles. We know that, remember, in the applied magnetic field from the spectrometer. Each of these protons will either be spin up or spin down. Well, at least that's the way they tend to align. So because they have their own little dipoles, protons are acting as tiny little magnets. And because each proton acts as a tiny little magnet in the applied magnetic field, they affect, protons on adjacent carbons that is, affect the magnetic environment of the observed protons that we're getting our resonance for in the NMR. So in other words, each of these 3 protons here is like a little magnet that affects the magnetic environment of these protons. Similarly, these 2 protons are like little magnets that affect the magnetic environment of these protons. And remember, anything that affects that magnetic environment affects the gap between the 2 spin states, the energy difference between the 2 spin states, spin up and spin down, and that affects the frequency of the resonance, that Larmor frequency we talked about in the first video. So I have a splitting tree for both of these protons down below to show you what's physically happening here. So for these 3 protons, so I've color-coded this tree is for these 3 protons here. These three protons are giving us a triplet, but they're splitting these 2 protons into what's known as a quartet. So 3 peaks like this is a triplet, this is a quartet, 4 peaks, 4 resonances. So these protons, since each of these protons can be either spin up or spin down in our applied magnetic field, there are a bunch of different possible orientations for these three protons in different molecules. In one possible orientation, all three of those protons are spin up, that is in the same direction as the applied magnetic field. In another orientation, all three of these protons are spin down. But those are the least likely of the combinations. Okay, so, and before I go on to that, the ones where all three of those protons are spin up, these are reinforcing the field, and therefore that's going to strengthen the environment, the magnetic environment of these two protons, and therefore that case gives us the farthest down field of the peaks in our quartet, of the resonances in our quartet. The arrangement where all three of these protons are resisting or going against, are aligned against the applied magnetic field, will reduce the effective magnetic field on these two protons, and therefore that will give us this highest frequency, or lowest frequency rather, highest field of the resonances in our quartet. Now the two central ones here, notice, are bigger. The ratio here is 1 to 3 to 3 to 1. So in this case, we have always have two protons aligned against the magnetic field and one aligned with. Here we've got two protons aligned with the magnetic field, the applied magnetic field, and one against, and there's three possible orientations for both of those situations. Since there's three possible orientations for these two, where we have some of the protons aligned and some aligned against the field, these central resonances of the quartet are larger, are more intense than the ones on the side, because there's fewer possibilities for these alignments than there are for the alignments where you have some of the protons aligned with and some of the protons aligned against the magnetic field. And so for these two protons, because the protons on the adjacent carbon can have all of these different spin arrangements, these two protons are affected by the different spin arrangements on this methyl group in this manner. And so we get a quartet for these two protons. It's the protons on adjacent carbons that split the observed protons because of the possible orientations of the spin states on those adjacent carbons. Those orientations affect the magnetic environment of our observed protons. So these methylene protons are a quartet based on these possibilities of the spin states of the protons on the neighboring methyl group. A little bit complicated, but if you think about it, hopefully you'll get this idea. Similarly, if we now observe the protons on the methyl group, there are two protons on the adjacent methylene. So these are the possible orientations of the spin states for these two protons. And these different orientations will affect the magnetic environment of these observed protons in this manner. So we can have two of these protons aligned against, and that will give us this highest field of the resonances in the triplet. There's two possibilities for having one proton aligned with the field and one proton aligned against the applied field. And so that gives us the central resonance of this triplet. And then there's one possibility of having both of these protons aligned with the field, and that's deshielding. And so that's the most deshielded possibility for these protons. And so that resonance will be the highest or the lowest field in this triplet. So because of these possible spin states on these two adjacent protons, these methyl protons appear as a triplet, the ratio being 1 to 2 to 1. The ratio of the integrations of these three resonances in the triplet. So this is the basis for spin-spin coupling. Now, types of coupling. We see here this is one type, this is a quartet, this is a triplet, that's another type. And you might be able to figure out from what we've discussed here the type of splitting that we'll see based on the number of protons on an adjacent carbon. So, it's known as the N+1 rule. N equivalent protons, that means in the same chemical environment, on an adjacent carbon results in N+1 resonances for an observed proton. So, here we have, in this table, the first column of this table, the number of equivalent hydrogens or protons on an adjacent carbon. If there are no protons on an adjacent carbon or adjacent atom, then there's no observed splitting, and what we see is a single resonance, and that's known as a singlet. So that's a single resonance for a singlet. If there's one proton on an adjacent carbon, and this also works sometimes for heteroatoms, you could have a proton on an oxygen or a nitrogen, or for example, that might split your observed proton on a carbon. One proton on an adjacent carbon gives us a doublet, n+1, and a doublet has two resonances. We'll see an example of that in just a moment in an actual spectrum. And I just go through these two protons on an adjacent carbon, which is what we saw up here. Okay, 2 protons on this adjacent carbon splits these protons into a triplet. That's 3 resonances. And then, to finish, to round out our table, 3 protons on an adjacent carbon gives us a quartet, which is 4 resonances, which is the other case that we saw here. So we have 3 protons on this carbon, so when we observe these, we see a quartet. So 3 plus 1 is 4 on these 3 adjacent protons, equivalent in the same chemical environment, plus 1 gives us a quartet for this for the resonance for these methylene protons. So that's the n+1 rule. I should point out here that this is known as a first-order approximation. There are more complicated cases where this rule breaks down, and we'll probably see some examples of those. But to figure out coupling in more complicated cases where you have second-order effects going on is beyond the scope of this course. It usually takes computers and calculations to be able to deconvolute those types of splitting patterns, although pattern recognition is very important in spectroscopy, and you can begin to recognize different types of patterns for second-order splitting patterns that in your mind you can associate with different types of structural features. But that's beyond the scope of this course. One more thing I should mention here is that sometimes you have protons in different chemical environments or on different carbons, on different atoms that are splitting your observed protons. In those cases, you might see something. If there are 5 adjacent protons, you might see 6 peaks, septet for 6 adjacent protons, for example. I often just refer to those splitting beyond quartets as multiplets, and sometimes they're very complicated, and if you get a complicated splitting pattern, the easiest thing to do is just call it a multiplet. For another example of some splitting patterns that we haven't seen yet, I have the spectrum, the Proton NMR spectrum for 2-bromopropane. And again, I've color-coded the protons. There's 2 different types of protons, the 2 protons on the 2 methyl substituents, and then the single proton on the central carbon that's bonded to the electronegative bromine. And as we would expect, this proton is farther downfield than the methyl protons are because this proton is on a carbon bearing this electronegative bromine. So that moves the chemical shift downfield. So if we look at the splitting here, each of these methyl groups is in the same chemical environment, so the chemical shift is the same. They're both coupled to this single proton here. Remember, when there's one proton on an adjacent carbon, the n+1 rule says that we should see a doublet for these identical protons here, and that's exactly what we see. There's our doublet for the methyl protons. Each of these 2 sets of methyl protons in identical environments are being split into a doublet by the single proton on this adjacent carbon. Now, it's a little bit more complicated for this single proton here because it's being split by these 3 protons over here and these 3 protons over here. And that's a total of 6 protons, so by our n+1 rule, we expect to see a septet, which is what we see here. Now I have to caution you, if we count these, there are 7 resonances here, as I was careful to draw. But you have to be careful because often when you start getting lots of coupling like this, you start getting these multiplets. Sometimes notice how the intensity trails off because of the statistics of the possible configurations of the spin states on all these protons. As you get to the edges of the multiplet, you're less likely to have those configurations, and therefore the intensity of those resonances is less. Sometimes these things are hard to see and sometimes they don't show up at all. Sometimes with multiplets, these things will begin to overlap, so you might not actually see a septet here. You might see fewer peaks than you would expect based on the n+1 rule. If these two methyl groups had been in different chemical environments, you can get more complicated splitting here. So again, often anything beyond a quartet I simply refer to as a multiplet. So finally now, to conclude our discussion of Proton NMR, I'll wrap up with some important points about spin-spin coupling, splitting. First off, chemically, and I've kind of alluded to this previously, chemically equivalent protons do not couple. We've actually seen that. I don't know if you've noticed that, but we've seen that in these spectra. So what we see for, again, what chemically equivalent means, you're in the same chemical environment. I should probably say, or usually, often, I do say that, often do not couple. In the cases that we'll be focusing on in our simple spectra in this course, this will usually be true almost always. So protons on methyl groups don't couple because they're in the same chemical environment. Why are they the same chemical environment? Because there's free rotation around that carbon-carbon bond there, which equilibrates on the NMR timescale the chemical environment of all three protons on a methyl group. So methyl protons occur as a singlet. What I'm saying here is they don't couple each other because they're in the same chemical environment. They're chemically equivalent. We see the same here, the same thing for ethane here. These two methyl groups in ethane the methyls are on identical chemical environments. So you see a single singlet for all 6 protons in methane. Cyclohexane, all 12 hydrogens are in the same chemical environment. Again, I should mention that you've got axial and equatorial, but those axial and equatorial protons are interchanging rapidly at room temperature on the NMR timescale, and so you see one singlet. Interestingly, if you take a spectrum of cyclohexane at very low temperatures, well below 0, that interconversion, as the temperature drops, slows down and eventually gets so slow that the barrier to the interconversion between the two chair conformations, that ring flip that we talk about with cyclohexane, stops, and you'll see 2 different resonances for the protons in cyclohexane, but at room temperature we see one singlet. The chemical environment of all 12 protons equilibrates. It's all the same, so there's really no splitting that's observed. Another very important concept: coupled sets of protons have the same coupling constant. Coupling constants are given the symbol J. So what in the world does this mean? Returning to our spectrum of bromoethane again, we've got our triplet and our quartet. I've expanded the triplet and quartet down below here. So here's our quartet, here's our triplet. The coupling constant is the distance between the resonances in these split peaks. So in our quartet here, the distance between each adjacent set or each adjacent resonance is 4 Hertz. Now that coupling, and that's known as a coupling constant. Now that difference between these resonances depends on the strength of the splitting, which depends on the chemical environment and how far the protons are apart and that sort of thing. So you get characteristic coupling constants for different types of coupling. So it's not always 4 Hertz, in other words. But here we measured it as 4 Hertz. So what is the coupling constant for the triplet? It's exactly the same 4 Hertz. It has to be, because when 2 sets of protons are splitting each other, they have the same coupling constant. This is the notation that we normally use here. So JAB, we've labeled often in NMR spectra and structures, we label the different types of protons. So the methyl protons we've labeled as A, the methylene protons as B. So the coupling constant JAB is 4 Hertz, and it's the same 4 Hertz in both the quartet and the triplet. This is really powerful for structure determination, because when you have complicated molecules and you have lots of different coupling going on between different protons in the molecules, you can tell what is coupled to what, and that tells you what is adjacent to what in the molecules. So very important to understand this when two sets of protons are splitting each other, they have the same coupling constant, the same distance in hertz between the peaks of each, between the resonances of each of the multiplets. Finally, one last thing. Protons on heteroatoms. And recall, by heteroatoms I mean any atom other than carbon, oxygen and nitrogen being the most common ones in organic chemistry. Protons on heteroatoms sometimes couple, sometimes split adjacent protons on carbons, and they can be broad. That is, the resonance is often not sharp, it's often broadened. Why is that? Protons on heteroatoms, as we've seen and previously in the semester, are acidic. They tend to pop on and off in solution, so we have this equilibrium going on in solution. The equilibrium constant for this equilibrium depends on the NMR solvent and the conditions and lots of things. It depends on the structure of the molecule, how acidic the molecule is. It turns out that if this exchange, and this is known as exchange or proton exchange, this proton's actually not going off by itself, it's being exchanged with something, there's some molecule, solvent or something in the solution that's accepting the proton. So in this exchange, if this exchange equilibrium is rapid, let's talk about if it's slow first. If the exchange is slow, that means the proton spends lots of time on the heteroatom. If it spends lots of time on the heteroatom, that gives it an opportunity to couple. That's slow on the NMR timescale with any adjacent protons. That's when you tend to see splitting. So if this isn't coming off very often, spends a lot of time here, it's going to be split by this adjacent proton into a doublet. This would appear as a doublet, the resonance for the proton on the oxygen. If, on the other hand, this is coming off rapidly, then it's not spending much time, the proton's not spending much time on that oxygen, and the splitting disappears. And so if you see a resonance at all for this proton, and you might, it tends to broaden. The more this pops on and off, it tends to broaden. So the broader it is, the more acidic it is, the more often it's coming off in solution. And so if it's popping off a lot, if it's not spending a lot of time on the oxygen, the coupling goes away and it broadens. And the more it comes off, the more often it comes off, the faster it comes off, the more that resonance will broaden. And sometimes it will get so broad that it's impossible to see, it just disappears. So if the proton on a heteroatom is acidic, if it's coming off rapidly, the coupling disappears. The faster it gets, the broader that resonance tends to be. If it's really broad, you might not see it at all. And with that, hopefully we're ready to begin solving problems with proton NMR spectroscopy, which we'll do in class. If you have questions over any of this, please ask.